So in this video, I'm going to talk about a special function, which is we call a common logarithm. So it's basically a logarithm with the base 10. So let's say we have the logarithm with the base 10 of, let's say, I don't know, like x equals something. Okay. And then when you have the base 10, we just don't write it. So instead of writing this way, we usually keep it as the log of x is actually equal to y. Okay, so whenever you see nothing as base, that basically means 10, and then we call that common logarithm. Okay, so that's something. And also, if you remember the exponent functions, like this is the graph of the exponential function when the a is equal to 10. So you can just see these 2 points will be on this graph. And another thing that we actually should remember is the exponential functions and logarithmic functions are inverse of each other. So which is why when you know the graph of the exponential function, you can actually take that function and find the inverse by taking the symmetry on the y equals x line. Okay, so they are going to be reflected on that line basically. So if you know the graph of the exponential, so you can just reflect over the y equals x line. That is going to be your logarithmic function graph. So this is the case always. And when you have two functions are inverse of each other, so if two functions are inverse, so they are actually reflect over the y equals x line. So that's something we see in this case for the logarithmic function as well. But the goal is in this video actually to graph and find out some key features of a logarithm function that has a base 10. So let's get started with that one, okay? So what I like to do now, I just like to have the function f of x, okay, equals 3 times the log like base with 10, but I'm not going to write that 10 of x minus 1. So let's think about this function, and then we will try to see some features of this one. The first thing we have to kind of come up with is the domain of the function. Okay, so the domain, you know, as the description, as a definition of the logarithm function, the argument, which is in this case x minus 1, has to be larger than 0. So from there, so you can see x should be larger than 1. So, but it can't be 1, so it has to be larger than 1. So if I want to write as internal notation, so this is going to be my domain. Okay, so that's one thing. But if you like to write in a different way, so we can just write as x such that everything that is larger than 1. So we are going to use this notation. So this is another way to write it. So the meaning of this and this is the same thing, okay? So that's the domain, okay? And if I like to graph this logarithmic function, we have to kind of find some key points. But before we do this, I will just, like, we can explore this couple different ways, but one of the good things about the transformation, using the parent function of any function, you can actually find the more complex version of those functions. So let's try this in this case as well, okay? So if I start with the graph of the, like just log of x, so let's try that. So I'm gonna do graph of this one first, right? So let's try that. Okay, so think about this is the graph. Most of the graph part will be on the first quadrant, so which is why I just draw this way. So if you start with y equals the log of x, right? So you can just remember, like, this guy can't be 0. So if this result is like 0, y value is 0, so the 10 to the 0th power will be the x, which is going to be 1. So you could see x is 1, y will be 0. So this is going to be 1 point. And you can just ask yourself what power of 10 is equal to x, which is just another way to writing this exponential, but I don't want to write it. I just like to get those values from the logarithmic function. So that's 1 point, 1 comma 0. Okay, so if you like to find another point, maybe you can plug the base, like, I mean, not base, but the y as 1 over 10, because 10 to the 110 is something we can try finding as well. So if I, actually, let's plug y is -1, that will be much better. If I plug -1 for y, so this is the base 10, so 10 to the negative first power is 1 over 10, so x will be 1 over 10. So if your y is -1, then x will be 1 over 10, so it's gonna be something right here. So if you choose y as -2, you will get 10 to the negative second power, which will be 1 over 100. So x will be getting smaller and smaller as you choose y values as smaller, right? So, but if you just increase the other way around, so if you're choosing some maybe y as maybe 10, okay, if this is 10, 10 to the 10 will be like a huge number, which will be a big number, so we don't want to write it. So, but it looks like the graph is gonna be like this. Okay, so this is the graph of y equals the log x. Okay. Again, I hope you do remember this one. So I'm gonna just write another point just to kind of remind. So if x is 10, so what power of 10 will be 10? So it will be just 1. So the corresponding y value should be 1. So if I say this is the another point on the graph, so you will get 3 points. Okay. So that's the graph of the log x. Okay. But what we are gonna do, we are gonna find the second graph by using this and some features of the transformation. So let me try that as well. Okay, so and then I will get this guy. So what we can do now, instead of dealing with the log x, I can find the log of x minus 1, right? Actually, let's try this. Yeah, actually, x minus 1 is also fine. So if I do x minus 1, meaning that your graph will be translating to the right by 1 unit. So instead of approaching to this line, so we are going to approach to this next line, which is going to be x equals 1 line. So let's try to see that as well. Okay, so this gonna be your asymptote, which is your line is approaching to. And instead of 1 comma 0, so you will move this 1 unit to the right side. So that should be another point will be right there. And if you move this one more unit to the right, so you will get 11 whatever. So that should be 11, maybe 1 right there. So you will be another point. And then it's gonna be similar to this graph. Only thing is just you are moving like 1 unit to the right. So it will be like this. Okay. So this is gonna be graph for y equals the log of like base 10 of x minus 1. Okay, so this is something, right? So we have, but how this is gonna be useful for 3. So if you remember the 3, the number that you multiply the whole thing to get your corresponding y value, so which is actually you are gonna vertically stretch the function. So let's see how that looks like as well. So if you are struggling with these each time, like using transformation, maybe it's better to review the transformation properties as well. So what we have now, you are gonna start with still the same point that we had right here, which I didn't write it, but that's 2 comma 0. And then this was 11 comma 1. Okay, so but if you multiply this log by 3 now, so let me write this as well. So y equals 3 times the log of x minus 1. So you are going to stretch vertically by the scale factor of 3, right? So, but your vertical asymptote, which is the x equals 1, okay, x equals 1, is not going to change. So that should be still the same. Okay, but this point will not change either. So this was 2 comma 0. So I'm going to write 2 0. But the y values will be triple. Okay, so instead of like now 10 comma 11 comma 1, so it was 11 comma 1, so let's say this is 11. Corresponding y value will be 3 and as of now, so it should be something like this. So it will be like stretched by a scale factor of 3. So basically, okay, so let's try to make a nice curve. So it will be something like this. Okay, it's not really a perfect graph, but at least it will tell us how things are going to look like. Okay, so far we got the graph, so I hope that makes sense. And then you may get this graph by reflecting the exponential function of the inverse of this guy, and you can reflect over the y equals x, which we'll see at the end, I guess, as another way. So that's something. We got the graph. So from graph, so we can determine some stuff. So we can see the range of the function that we have. Okay, so and then we can kind of talk about the vertical asymptote as well. So the range of this one, right? So the range is equal to, as you see, it goes all the way to the like negative infinity and increase all the way to positive infinity. So the range is all positive integers. So if you like to write as integer notation, so you should get negative infinity, positive infinity. So that's gonna be the range. Okay, so the vertical asymptote is x equals 1. So if you see this line, so this was my vertical asymptote that the graph is getting closer and closer. So the vertical asymptote is x equals, this was x equals 1, right? Okay, so that's the vertical asymptote. What else can we find? So we may find now the inverse of this function. All right, so let's try to find the inverse of the log function that we have. So to find the inverse, you know, the x and y just swapping. So they just change the role basically. So what we were given was like y equals 3 times the log base like with base 10 of x minus 1. So I'm gonna just write x minus 1 for now. And then you are gonna just swap those x and y. So that should be x equals 3 times the log of my y minus 1. So your goal is to get this y alone, but you cannot do that when you have this product. So let's divide both sides by 3. So let's divide by 3. That should give me the log of base 10 of y minus 1. But it's good to write this 10 if you don't see it. So I will just say this is 10, but you can just leave it without writing. The reason I'm writing this because I like to convert now into exponential. So this is my base to this power. So let's write that way. So 10 to the x over 3 is equal to y minus 1. If you add 1 to both sides, so you will get y equals 10 to the x over x third and plus 1. And then this is the function will be inverse of the function that we start, which was like this guy. So if I say what would be the f inverse of x, then I will say that's equal to x 10 to the x over 3 and plus 1. So this function is my exponential function, is the inverse of this logarithmic function. Okay, so we got the inverse as well. So, but what can we say about this function? So we can talk about the domain and the range of the inverse function. So since they are inverse of each other, like this log function and the exponential function are inverse of each other. So domain of the f, so maybe I should highlight that as well. So domain of f is equal to the range of f inverse, or the range of f is equal to domain of f inverse. So why this is important, or why this is the case? Because you're just swapping the roles. Like whatever we had domain of this actual function that we start with, which is, you know, if you look at the domain of this function, everything that is larger than 1 was a domain So domain of this function, this graph will be range of the inverse function. So range of this guy will be anything higher than 1. So you can actually see that, you know, if you choose some values of x right here, so if you choose like x to smaller negative values, let's say negative 10,000, 10 to the negative 10,000 divided by 3 will be 10 to the a negative number, but the power is like bigger when you do that. So you'll get 1 over 10 to the some exponent that will be getting smaller, like, and smaller if you choose x to be too small. So this guy will be 0. 0 plus 1 is getting closer to 1. So which is why your function actually getting closer to 1, but anything you choose higher and higher, so this getting bigger and bigger. So everything larger than 1 is actually going to be your range. So the range of the inverse is going to be a domain of the function that we start with, or the other way around. So the range of the function is the domain of the inverse. So we can just say those as well. And as a last step, we can maybe graph the this function as well. You can just plug some values to graph it, but I like to kind of use our relation between the inverse graph and the function itself. So I have to graph the y equals line. So let's do that. So this is not y equals y, y equals x, right? So this is the, okay, I missed that. So let's try this way. So this is the y equals line, y equals x line, y equals x. So when I graph the function and inverse, they are gonna be reflect over this line. So if that's the case, let's try to see some points. This is 2, 0, so they will swap the role. So that will be 0, 2. And then you had 11, 3, so they will be 3, 11. So that should be 11. And then like 11, 3 will be here. So I don't know if I have enough space, but it will be, okay, 3, 5, 6, 8, 10, 11, something like this. Okay, right. And then this is like x equals like x equals 1 is my vertical asymptote, right? So if this is my vertical asymptote, my horizontal asymptote will be y equals 1 for my inverse function, because the vertical and horizontal asymptote will swap as well if they are inverse of each other, meaning that your graph is going to be getting closer to this line. Okay. So it looks like my graph will be like this. Okay, so that should be going this direction and this direction. And if you look at my two graphs, this red line, I mean curve, and then this green curve, they are actually looking like reflect over this line, which is a good sign that we actually got the correct graph. So I hope that makes sense. So this is our I guess general ideas about the graphing logarithmic function and the relation between exponential and logarithmic functions. Okay, so I'll see you in the next video.